Hello everyone, and welcome back to Path Finders Analyst. I hope you are doing well. In today's video, we are going to discuss three very important concepts from econometrics. First, we will understand the classical linear regression model, or CLRM. Second, we will understand the normality condition, how it is incorporated into the regression model, and why it is important. And finally, we will discuss the properties of OLS estimators under the normality condition. So let's understand each concept step by step. 1. Classical linear regression model. Let's begin with the classical linear regression model. The basic idea behind regression is that we want to understand the relationship between a dependent variable and one or more independent variables. For example, suppose we want to understand how income is related to years of education. Here, income can be our dependent variable, y, and years of education can be our independent variable, x. The simple linear regression model can be written as y equals plus x plus u. Let's understand each component. Y represents the dependent variable. X represents the independent variable. Is the intercept. It represents the expected value of y when x is 0, subject to the model interpretation. Is the slope coefficient. It tells us how the expected value of y changes when x increases by 1 unit, holding other factors constant. And finally, u is the error term. The error term is extremely important because we cannot normally explain every factor that affects y using the variables included in our model. For example, when explaining income using education, income may also depend on experience, skills, location, industry, family background, and many other factors. If these factors are not explicitly included in the model, their combined effect is represented through the error term. So, the regression model can be thought of as systematic part plus unexplained part. The systematic part is explained by our x variables, while the unexplained part is captured by the error term. The objective of OLS is then to estimate the unknown coefficients, such as n, using sample data. 2. What is the normality condition? Now let's move to the second concept, the normality condition. The normality condition tells us that, conditional on the explanatory variables, the error term follows a normal distribution. We can write this as ux tilde n, 0, squared. In simple words, the errors are distributed around 0 in a bell-shaped pattern. The mean is 0, which means that the errors do not systematically tend to be positive or negative. The variance is squared, which represents the spread of the error distribution. Now, there is an important distinction here. Normality itself refers to the distributional shape of the error term. The assumption of 0 conditional mean and the assumption of constant variance are separate assumptions. However, when we write ux tilde n, 0, squared, we are combining these properties into one distributional statement. This additional normality assumption gives us the classical normal linear regression model. We start with the classical linear regression model. Then we impose the assumption that the error term is normally distributed conditional on x. And the resulting model is called the classical normal linear regression model. 3. Why is normality important? Now the obvious question is, why do we need the normality condition? OLS can still have important properties such as unbiasedness and consistency without assuming normality, provided the relevant classical assumptions hold. So normality is not what makes OLS unbiased. Instead, normality becomes particularly important when we want to make exact statistical inferences in finite samples. For example, suppose we estimate a coefficient and want to know whether that coefficient is statistically different from 0. We may want to perform a t-test. Or perhaps we want to test whether several coefficients are jointly significant using an f-test. We may also want to construct confidence intervals or prediction intervals. The normality assumption helps us derive the exact sampling distributions required for these procedures under the classical model. That is why normality is an important additional assumption. 4. OLS estimators under normality. Now let's come to the final and very important part of today's video, the properties of OLS estimators under the normality condition. Let's take them one by one. First, unbiasedness. The first property is unbiasedness. For an OLS estimator, we have E equals. This means that if we repeatedly collected samples and calculated the OLS estimate each time, the average of those estimates would equal the true population parameter. In simple words, OLS does not systematically overestimate or underestimate the true coefficient, assuming the required assumptions hold. And remember, this unbiasedness does not depend on the normality assumption alone. It comes from the relevant assumptions, particularly the zero conditional mean assumption. Second, efficiency. The second important property is efficiency. Under the Gauss-Markov assumptions, OLS estimators are blue. Blue stands for Best Linear Unbiased Estimator. Best here means that among the class of linear unbiased estimators, OLS has the smallest variance. So, if we have different linear unbiased ways of estimating the same coefficient, OLS gives us the estimator with minimum variance under the classical assumptions. Again, this property comes from the Gauss-Markov assumptions and does not require normality. Third, normal distribution of the OLS estimators. Now normality gives us an additional and very useful property. If the error term is normally distributed, then the OLS coefficient estimators are also normally distributed in finite samples. We can represent this generally as tilde var. This is important because we now know the exact distribution of our estimator under the model. And knowing the sampling distribution allows us to perform statistical inference. Fourth, statistical inference. This brings us to the fourth property. Because of the normality assumption, we can derive the distributions required for t-tests and f-tests under the classical model. H equals 0. We can compare the estimated coefficient with its standard error and calculate a t-statistic. This allows us to determine whether the relationship represented by that coefficient is statistically significant. Similarly, when we want to test multiple restrictions or coefficients together, we can use an f-test. We can also construct confidence intervals around our estimated coefficients. So normality provides the foundation for many of the standard finite sample inference procedures used in classical econometrics. Fifth, consistency. The final property shown on our slide is consistency. An estimator is consistent if, as the sample size becomes larger, the estimator gets closer and closer to the true population parameter. We can express this as this means that the OLS estimator converges in probability to the true coefficient as the sample size increases. Again, consistency does not come simply from assuming normality. It depends on the appropriate conditions for consistency being satisfied. So, normality should be viewed as an additional distributional assumption that gives us stronger finite sample results and facilitates statistical inference. Final summary. So, let's quickly summarize everything we discussed today. We started with the classical linear regression model, which describes the relationship between a dependent variable and one or more explanatory variables, together with an error term. Then we introduced the normality condition, where the error term is assumed to be normally distributed conditional on the explanatory variables. When this normality assumption is added to the classical regression framework, we obtain the classical normal linear regression model. Finally, we discussed the properties of OLS estimators. Under the classical assumptions, OLS estimators are unbiased and efficient, meaning they are blue. With the additional normality assumption, the OLS estimators have a normal sampling distribution in finite samples, which allows us to derive the standard distributions used for t-tests, f-tests, confidence intervals, and hypothesis testing. And with the appropriate assumptions, OLS estimators are also consistent, meaning they converge toward the true population parameters as the sample size increases. The key point to remember is that normality is mainly important for obtaining exact finite sample inference, while properties such as unbiasedness, efficiency, and consistency rely on their respective underlying assumptions. I hope this video helped you understand these concepts more clearly. If you found this video useful, please like the video, share it with your friends, and subscribe to Path Finders Analyst. We will continue covering important concepts from econometrics, statistics, Python, SQL, Excel, and data analytics in upcoming videos. Thank you so much for watching. Keep learning, keep practicing, and I'll see you in the next video.